All right. Good morning, everybody. Hopefully we're all doing well after our Cinco de Mayo hangovers. Yes, I got coffee. That's the cure for everything. Okay. Just some quick announcements for the class. We're going to continue our discussion on fracture mechanics today and maybe into Friday. I think kind of the material that we have today and going into Friday is kind of interesting stuff. It's all about how to increase fracture toughness of composite materials. So these are all common things that people do in industry now to increase the toughness. And so it'll be some qualitative discussion about what people are doing to increase that toughness. And I just think some kind of like cool, interesting tricks that people are playing in the real world to increase the toughness of what are generally like these brittle composites. All right. So I anticipate maybe today and tomorrow finishing up fracture, and maybe on Friday starting in on the next topic, which I think will be woven composites. I want to do just one quick day or like a day and a half on woven composites. So we haven't talked much about woven composites in this class, and I want to make sure to get that as something that's on your resume. So we'll talk about woven composites a little bit. It's pretty simple, nothing more complicated than what you can already handle. It's just we got to talk about it a little bit. Or in the spirit of yesterday, we got a taco about it. Okay. Right. Then I wanted to talk about sandwich structures, so that'll be the last major topic for the class. I want to give maybe 3 days to that on manufacturing methods and differences in analysis that are required for sandwich composites because they're kind of complicated. I want to give 1 day for review, and then it's the final test. So not a lot of time left for us. Right near the end, I'm proud of how you guys have handled the class so far, and keep it up, okay? Rawr. All right, all 7 of you that are out there in the audience, good job. All right, so without any further ado, if there aren't any questions, we'll get moving on some material. All right, so we're in the middle of our fracture mechanics discussion. And we really were looking at mode 1 fracture of composites. So I kind of showed some real life pictures of the tests that were in action for this mode 1 testing of composites. So I just want to like reiterate what those look like. Is that you've got a sample that somehow looks like this, which is the double cantilever beam sample. So that looks like this. Okay, and I showed what one of these is kind of in my hands in class on Wednesday, right? So I've got one here. I wish I could pass it around to you guys, but I can't because then we would all get a virus, and that's bad. All right, but the general idea here is that you've got this composite that is here. All right, maybe I should do that black, should do that in red. Here is the composite that you've created. And then you put into it a pre-crack, which is here, this sort of like initiation crack here, usually with some Teflon, some thin Teflon piece during the manufacturing process. And then you apply piano hinges to it here by like gluing them on or epoxying them on. And then when you pull on those piano hinges, the sample opens up in mode 1. All right. So when you pull on those hinges, you get something that looks like this. Where here we have things like initial crack length. Here, this is the applied load. Here, this is crosshead displacement. And here you have width. All right, so these are the common sample geometries for mode 1 fracture testing. If you ever do mode 1 fracture testing of composites in your life, you will make a zillion of these. Okay, graduate school, I probably made, I don't know, 300 of those things, maybe more. Yeah, many, right? Okay, so there you go. That's double cantilever beam specimen. When you pull on that and you test that, what you're going to do is you're going to track the crack and how the crack propagates on the side of the sample, and then marry up crack advance with load and displacement to calculate critical strain energy release rate. So data that might come from that is going to look like this. All right, we're in black here. We have the load displacement curve. So we're loading, 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 loading. And then at some point, we're getting to a point where the crack is now going to propagate. So we're pulling, 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 pulling. And then all of a sudden, we get some crack advance starting to happen. And so right when this point occurs, the sample is relieving itself by creating a free surface. And so we're moving down here and we're looking at, all right, what is the current crack length? So that's kind of the right-hand side y-axis here, as we are opening the sample up. Okay, so you can match each one of these like 5 millimeters of crack advance with a various load displacement value. So here's my load displacement value for a crack length of there, and you can use all this information to calculate the critical fracture toughness of the ith event, which we said was GCI, here equal to 1/2 times 1 on B times delta A multiplied by PI delta J minus PJ delta I. All right, so there's your fracture toughness, your critical strain energy release rate at each individual event. And from there, you can construct the R curve, which plots the crack advance delta AI versus GCI. And this gives you a lot of general information about what's happening with the sample. And that R curve looks something like this. All right, so this is an example R curve. Notice here that it is generally flat. Okay, indicating that we have like an elastic material. All right. And typical values for critical strain energy release rate of composites are anywhere in the like 200 to 1,000 range. So here you see 200, and this is specifically for an 8 harness satin weave glass epoxy composite, but it can be, you know, this guy's maybe got an average of like 410, something like that. So you get the general idea of approximately what these values are. And remember here, it's in units of joules per meter squared, the amount of energy required to open a certain crack opening area. All right, so there we go with some mode 1 fracture testing to determine critical strain energy release rate. And I promise you, if you do anything in composites developing new materials, you will do so many of these tests. You will be sick of them by the end of your life. You're going to be gluing piano tabs on from now until forever. All right. So that was all sort of mode 1 stuff. We did an example problem and sort of looked at how this might actually proceed. And I realized there was kind of like a mistake in the order of magnitude of the example problem. So I was kind of in the process of uploading or re-uploading the notes when lecture started. So right after lecture, I'm going to upload some new notes where that example problem is sort of straightened away. Okay, so I'll make a note here. New notes with amended example problem coming. And I'll have that up by 10 Central today, so just give me a little bit of time. All right, so moving on. That was mode 1 testing. Now we want to go to mode 2 testing. All right, and so mode 1, we had the double cantilever beam specimen that was the specimen of choice. And I'll say here, the most common specimen for mode 2 test is what's called the end notch flexure or edge notch flexure. All right. All right, often abbreviated ENF. All right, so let's take a look at what that sample geometry is. All right, so the geometry looks something like this. All right, so this looks a little bit different than the mode 1 test. So the mode 1 test, you just take this guy and sort of like pull it open in tension, okay? For the edge notch flexure, you're actually putting this into a 4-point bend or a 3-point bend configuration. So here we have 3-point bend configuration. and that's called the 3ENF. And then here we have 4-point bend. Or what we can see here is 4ENF, right? Edge notch flexure or end notch flexure. So the idea behind this particular geometry is that end notch flexure. All right, so here we put our starter crack on the edge of the sample and move its way in, right? That's the general idea. Both of these samples have the same sort of general idea, is that you have the starter crack that starts at the end of the sample and moves its way in. So the samples look basically exactly the same as the double cantilever beam specimen. You've got the starter crack, which is initiating from one of the thin edges and moving its way in. All right, that starter crack is usually made by inserting a piece of Teflon or thin film during the manufacturing process of this particular laminate or woven structure, right? So you have that starter crack in there, and that initial crack length then here is a knot. And that initial crack length is the distance between the pin where this guy is loaded and the edge of the crack, all right? So here we have our loads. Here's P on 2, here's P on 2, and here's P, which is sort of being applied to this particular specimen. All right, so what's going to happen here is just like the deck of cards example. I got them today. All right, so I'm gonna move to the document camera. Actually, my laptop camera. Where's Teams? Where are you? Okay, I have things today. Props. All right. So this is a stack of cards, right? The idea here is that if I put this thing into a 3-point bend, which I'm going to do right now, each one of those layers is like sliding against each other. Okay, might be a little bit difficult to see, but hopefully we can see that. Those layers sliding against each other is the mode 2 type of like failure that we're looking to achieve. So what's happening here is that this like sliding shearing mode is activating, especially at the midplane. All right. So remember that our mode 2 looks something like this. I'll bring in the picture just to remind you our different failure modes. So here's the mode 2. I'm going to take this away in just a second, so don't worry about copying this down. But here is this mode 2. All right, and it's like sliding against each other. All right, and that's what we're trying to achieve by putting this into bending, is getting those layers to slide against each other kind of in shear. All right, so that's what's happening with this edge notch flexure sample. Is right at the midplane here, like these guys are trying to slide against each other like this. All right, that's that kind of like shearing type failure. All right. So you can do this in 3-point bend, you can do this in 4-point bend. 4-point bend is more common because of how the stress distribution is distributed inside of the piece. Okay, but generally they're more or less the same. All right, so these are the general samples and what they look like. Okay, back to it. The same idea kind of holds here, is that when we apply this bending load, we're going to supply energy to the sample. All right, so analysis is more or less the same. I'll say 4ENF is more commonly used. And that's because more stable stress state. Okay, just to remind you what it means to be in 3-point or 4-point bend, if you go back to your bending moment diagrams. Okay, so here's like the moment as a function of x. Here's the moment as a function of x. This is for 3-point bend. This is for 4-point bend down here. Your bending moment diagram for 3-point bend looks something like this. Okay, for 4-point bend, it looks something like this. All right. So what I mean by it's more stable is that if you're trying to propagate a crack in 4-point bend, if you have a stress state that is constant inside of this region, it's much more easy to handle. All right. As opposed to, let's say my crack is here and then it's moving a little bit. Now it's here, moving a little bit. Now it's here. Well, I'm changing the stress state at that particular piece in those particular locations. All right. So not so great. And since we're, a little bit more concerned about shear, the shear diagrams are also telling. Okay, so remember your shear diagram, something like Vx for 3-point and 4-point bend. For 3-point bend, you have something that looks like this. And for 4-point bend, you have something that looks like this. All right. So remember back to your statics days where you drew these shear and bending moment diagrams. All right, so for 3-point bend and 4-point bend, you have moment and shear diagrams that look something like this. So it's a little bit more stable to be testing a composite and 4-point bend in like this region here, because your stress states are generally steady. All right, hopefully we sort of see and understand that. So 4-point bend, most commonly used. Now, the idea of what we're doing here is more or less the same. We're supplying or putting work into the sample by loading it, kind of in this bending mode. And the energy that we apply to it through the work process, this external work that we apply, has to be balanced by the elastic energy and the energy from fracture. All right, so we'll say if brittle, methods are the same. That is, the total work that we put in has to be equal to the elastic energy plus the energy of fracture. Right? Balanced by elastic and whatever work we did for fracture. Right? So the general idea here is the same. The energy of fracture is D is equal to the total work minus the elastic energy that we recover. It's the same general idea. And we saw this with the double cantilever beam specimen. Now, for simple tensile loading, the amount of work that you put in, easy. Right? We know that that is just like the integral of load displacement, d delta. All right, that's easy. Now, when we're talking about applying bending moments to a piece, the work that is now applied is more complicated, okay? And that's because we have different stresses at different points in the piece, and how do we handle that and how do we manage that? Well, you can go back to, maybe you talked about strain energy in 3005. I think they've cut strain energy out of 3005. It's a little disappointing to me. But there's a general expression for what the strain energy is if you apply various forces. So generally, we need, what is this total work term, to sort of solve the equation up here. All right, if we're trying to solve that particular equation, we need everything on the right-hand side there. All right, the elastic energy we recover, that's easy. That's just the load under the energy under the load displacement curve. This total work that we apply is going to be a function of the forces and the stresses that we apply. Okay, so we need some expression for that particular piece. And I'll say this expression for the total work in bending is complicated. We could plow our way through the algebra, plow our way through the integrals if we wanted to, and make our way through it, but I don't think that's really a useful exercise. Generally, the expression, because you have both a bending moment and shear, is something like the total work now not being the integral of the load over the displacement. It's actually the integral in the volume, or here this V is volume, of the stress in the x direction squared on 2 times the modulus in the x direction plus the shear stress that we apply now in xy, or in our case it's xc, on 2gxy. All right, this is the actual work that's applied if you have sample that looks something like this, and this is like the XY direction. All right. So if your sample geometry is there and that's your XY direction, this is your expression for the total work that's on the piece. That looks significantly more difficult and more complicated than what was the original expression that we had over here for the integral under the curve for the particular work. All right. So intention, it's easy to understand. All right. It's the area under the curve that is the total energy that's applied. All right. When we do bending analysis, that's not nearly the case anymore. It's much more complicated. And your notes actually goes through this to the other side. Notes expands on this. I don't think it's a particularly useful exercise to like go through what is the stress state, what is the shear, the normal and the shear stresses at the crack tip as this thing is going through, and then write them in terms of like sample geometry and all that sort of stuff. We could do that, all right, but I don't think that's a good use of our time. All right, so instead I'll kind of just cut to the chase. All right, I'll say cut to the chase. The idea is simplify the total work down to something in terms of loads applied and sample geometry. And then we'll normalize fracture energy by area created to get G to C. All right, this is the critical strain energy release rate in mode 2. Right. So I'm just going to present it here and kind of without full derivation, but hopefully we kind of get the idea of what's going on here. And that is for edge notch flexure testing with the geometry sort of described above. We have that G2C is equal to the following. Here we have 9 pi delta I AI squared over 2b, or not 2b, 2l cubed plus 3ai cubed plus here. And there's your general expression for critical strain energy release rate in mode 2 with an edge notch flexure sample. And this is good for 3 and 4 ENF. All right, so let's explain what these variables are. Obviously, G2C, this is the mode 2 critical strain energy release rate. It's kind of what we're getting after with this new geometry and this new type of test. All right, PI is the load on the sample just before fracture event I. All right, so again, we're going to kind of have these like discrete failure events. We're assuming kind of like a stick slip behavior. All right, and delta I. Here's the displacement on the crosshead just before fracture event I. So what I mean by crosshead is, if you're putting this thing into 3-point bend, your piston on the top has some displacement associated with it. This is that displacement that I'm talking about. The motion of basically the pin that's pushing on your sample. Displacement of crosshead just before fracture event I. Let's continue. We have some other things here that we can probably identify, and that's AI is the crack length. And I'll make sure that you know that this is the total crack length, not some crack advance. They're different. All right. The total crack length is wherever the crack is at that particular moment. Measured from outer pin. This is just before fracture event I. Continuing, B, obviously sample width. This is into the page. And then we also have L, which is the sample half span. So what I mean by the sample half span, we go back up to our picture, and we see that generally the sample has a width of 2L here. So L is the half span, half the distance between the outer pins on the sample. All right, so again, you see it down here. 2L is 100 millimeters. That means that the half span L is 100 millimeters. All right, so there's the general idea. This is the equation that you're going to want to use for homework problem number 3. And you're going to look at some actual data, pull off this load displacement and crack length data, punch it into that particular equation, and you should get some values of GC. All right, so there's your mode 1 and your mode 2 testing, the associated samples, and so on. Just like for mode 1, there is a standardized test for mode 2 fracture. So I'm just going to pull that up here really quick and share that with you guys as well. So let's do that. All right. All right. So here again is a standard. I've posted this on Blackboard. I really advise you to download this because it's not free. And if you go out in industry, people pay hundreds of dollars for this particular standard. So put it on your machine, take it with you. And if you ever need to do mode 2 testing of composites, this will be your Bible. All right. So mode 2 interlaminar fracture toughness of unidirectional fiber reinforced polymer matrix composites. So all the information is kind of here. And this is our sample geometry. All right. So we've got a cracked end here in the pre-crack on the left-hand side. And this is for edge notch flexure. So ENF, test fixture, and specimen nomenclature. So you see it here in the it describes everything associated. All right, so here again, it's indicating to you that the critical strain energy release rate, which is G, is 1 divided by the sample thickness, so 1 on B. And then DUDA is the amount of energy required to propagate the crack a certain amount. So same stuff we've been talking about. DU is the change in energy, DA is the change in crack length. All right, so this is exactly what we've been talking about so far. Additional information on sample geometry. It talks about the apparatus that you need, what testing machine, displacement rates in the range of 0.025 to 1.6 millimeters per minute. So it goes into everything that you could possibly need. Talks about the specimen geometry, should have a span of 100 millimeters and a nominal half span of 50 millimeters, so on and so forth. Okay, so all the information about sample testing is contained in this particular standard. It tells you everything that you basically need to know, including analysis methods and even up to like surface finishes for the pins and the surface of the sample. It's just like insane. All right. This is an example of low displacement that might come off from one particular sample. So here's an example of low displacement that you might see. All right. All right. So yeah, there's a standard. Download it, put it on your machine, make it yours. Own it. All right. There you go. As an experimentalist, I had those as my Bible. I prayed to them every evening. Oh, standards of testing, how I loathe thee. All right. Now, fantastic. Great. Marvelous. Let's get back to the writing pad. We've talked about analysis methods for mode 1 and mode 2 fracture of composites. Okay. And we generally understand that the matrix materials that make up composites are very brittle. And composites will generally fail in fracture before they fail in any of these other modes associated with like strength metrics. Okay, so the fibers that are inside of the composites are not really going to be the ones that fail most often. Usually it will be the brittle matrix phase that tends to fail because there's an initiated crack or a void inside your material where a fracture can initiate from, and all this sorts of crazy stuff. Okay, so because of that, people have looked at increasing the toughness of, let's say, the matrix material and thus the composite as a whole in a variety of different ways. So what I want to look at over the next, lecture and a half or so are kind of cool tricks and things that people have either identified or have leveraged to increase the toughness of these composites. So we'll look at a variety of different examples, and then what the general increase of each one of these examples might provide you should you choose to like pursue them. All right. So that's what's coming next. And I'll generally label this section toughening mechanisms. Good. So because composites are made with a brittle matrix phase, I'll say usually, methods for toughening have been pursued. All right. Those methods include, and I'll kind of go into depth on each one of these things. The first is not really a method that people have pursued per se, but is one that kind of naturally exists in composites, and we'll talk about this. It's called fiber bridging. All right. Another one we're going to talk about is matrix modifications. I mean, that one's obvious. If you can make a tougher matrix, then your composite generally will be tougher. All right, so fiber bridging, matrix modifications. People have incorporated stitching. Right, so if I stitch through my composite, it's going to help to resist the composite from opening a crack because I have these stitches that are moving through. Related to that is Z-pinning, which is a similar idea. Except now I'm not stitching, I'm just putting big pins right through the middle of the piece. There's an idea called interleaving. This one is interesting, and it's the inclusion of very thin thermoplastic layers between the composite laminate layers. So if you can incorporate, let's say, like a thermoplastic urethane between individual layers of the laminate, then you would really toughen up the interface between the two different layers. So that's an interesting idea, except there's a drawback there because it really decreases the overarching mechanical properties of the piece, and also architectural modifications. Oh, spelling is hard. Oh my gosh. I'm an engineer. Fabric. Architectural modifications. Yes. Okay. So what I mean by that is, can we change the weaving pattern or generally the stacking sequence of the laminate to increase our toughness, and how much can we really affect the toughness by, let's say, modifying the stacking sequence some amount? All right, so let's move, and we'll start first with this fiber bridging idea. All right. So obviously composites are made of, the composites that we talk about are made of like continuous fibers and like a matrix reinforcement. So for any kind of like two layers that are inside of the sample, we've assumed kind of in this class that two layers, when they separate, there is nothing that connects those two different layers. All right, we say, all right, the crack has gone through, they're completely separated. But in actuality, what happens is yes, the matrix will fail and the cracks will separate, but there will be some individual strands of fibers from the bottom layer which sort of migrated their way into the top layer, and vice versa. Is that there's fibers from this top layer that have kind of migrated into the bottom layer. And so what happens is, like, as you pull this crack open, there are still fibers that are hanging on from the bottom layer attached to the top layer. And there are still some fibers from the top layer that are sort of hanging on to the bottom layer. So think of almost like Velcro, okay, where these fibers are kind of like attached to each other through the crack. This is what's known as fiber bridging. So I'll bring in a picture of what this actually looks like. Right? So I'll write here for two layers in a composite undergoing separation through fracture. Some fibers may still bridge the gap. All right, this adds to the toughness because it's like those fibers don't want to let go. All right, this adds to like increase the toughness generally of the sample. And let's take a look at what this actually looks like in reality. All right, so here's kind of an example. This is a double cantilever beam specimen that's being pulled apart. So here, this is a, boy, that's really hard to see. Seems red. This is a DCB specimen, and it's being pulled apart here and here. All right, so it's being loaded in this general direction. What you see here in the center is all of these fibers, all of these guys right here from the bottom layer and the top layer, respectively, that don't want to let go of each other. All right, all these fibers are sort of commingled in that crack plane as you sort of pull this open. Like the example that we have here is very extreme, and I think that people that were actually doing this test really made it a point to try to increase that fiber bridging by like fluffing up the, you know, glass fiber mats that they were using to create this particular sample before manufacturing. So they really put a lot of effort into making this fiber bridging happen. But the general idea is there, is that like when you pull open this composite, there are fibers that sort of span this crack plane. So what happens when this occurs is these fibers sort of act to increase the toughness of the sample generally. All right. Now, what's interesting is that if I'm doing a test, I need to create a sample. All right. When I first create the sample, I do that by putting a piece of Teflon into my piece so that I have this starter crack that exists between two different layers. When I have that starter crack in there, there is no fiber bridging at that particular location. There are no fibers that are spanning that layer. I've made sure of it because I've included this Teflon piece. So when I first start the test, there is no fiber bridging. However, as I progress through the test, my fiber bridging is increasing and increasing and increasing because I am getting further and further away from that Teflon insert inside of the piece where the fibers originally were. So what this leads to is some interesting phenomena in the R curve for the sample. All right. Leads to, oh God, my spelling day. Leads to interesting results in the R curve. Remember which plots G1C versus the crack length AI, right? So remember that's what the R curve is. So let's take a look at what I actually mean here. Now here's an example of what I'm trying to describe. All right, so initially, so here we are, another double cantilever beam. This guy's being pulled open, this guy's being pulled open, and you see all the fiber bridging that's occurring like right at this particular location. So what I'm trying to describe here is that initially here is your Teflon. No fibers. And you can very clearly see that there's no fiber bridging that is occurring in that particular region. So you see this Teflon piece here. There's no fiber bridging that occurs there because you had the Teflon to interrupt it. So right when you first begin your testing, there is no fiber bridging. And what that results in is lower values of your critical strain energy release rate because you don't have this Velcro that's like holding on and hanging on to sort of cause the sample to stay together. Okay, so during beginning portions of testing, there's no fiber bridging. And therefore, G1C is lower. So as we progress, G1C increases as fiber bridging occurs. Hopefully we can all kind of understand that and follow that. Initially, there's no fibers bridging the crack plane, but as the crack begins to propagate, more and more fiber bridging will be apparent. Okay? So it results in R curves, which again is like plotting the critical strain energy release rate as a function of crack advance. It results in these R curves that look like this. All right, so this is sort of like real life data. And what's happening here is that initially when the test starts, so let's take a look at like this line, for instance. All right, so initially when the test starts, we're like here, and no fiber bridging has occurred. So my value of the critical strain energy release rate is relatively small. So this must have been like the initial crack length. Then as the crack propagates, more and more fiber bridging occurs, and it becomes harder and harder to open it because there's more and more of this bridging effect. And so what you see is this slow rise in the R curve until you get to some plateau, where this plateau now occurs when the amount of fibers that you're creating in your fiber bridging region is equal to the amount that have been lost from the back end of the testing. All right, so you have like, let's say you have 10 fibers that are holding on as you propagate your crack. If I propagate my crack a little bit more such that one more fiber is holding on and I lose one from the other end, then it's like I'm keeping this equilibrium of only 10 fibers that I have bridging my crack plane at any time. But when I first start, I have 0 fibers that are bridging the crack. And then as it propagates, I accumulate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until at the very front, I've now reached this equilibrium where I only have like 10 fibers that are holding. I mean, obviously it's a lot more than 10, but I'm just trying to like make an example here. And so here, this is an equilibrium. Where fiber bridging zone is constant. All right, meaning the amount of new fibers that are entering my bridging zone by crack propagation is the same as the amount that I'm losing from further upstream of the crack. All right, hopefully we can kind of understand that. So when you see this behavior on an R curve, it starts low and then it increases slightly. That's an indication that you have this significant fiber bridging that occurs. Right? So the actual critical strain energy release rate and what people will report is kind of an argument. But generally, the reported value is the plateau value. That's because in real life, you wouldn't have this Teflon inside of the piece. You're only using that Teflon to sort of initiate and propagate the crack. Okay, so you would have fiber bridging in real life, and therefore you want to see what this plateau value is because that's representative of the fibers that would hang on in real life. Right? So if you're doing this mode 1 testing and you see some behavior that looks like this, now you kind of understand what's going on there. All right, so that's R curve behavior for fiber bridging. I think that's where we'll stop today. We'll pick it up on Friday, talking about sort of the last toughening mechanisms for the class. All right, so thanks for coming, and we'll see you on Friday. Get your homework done. Rawr.